All right, so like I said, we're moving on to acceleration. We just looked at velocity and speed. And velocity is the rate of change in position with respect to time. Acceleration is another level up where it is the rate of change of velocity with respect to time. So again, just kind of in terms of real life language, velocity is how fast your distance is changing with respect to time, and acceleration is how fast your velocity is changing with respect to time. All right, and so because of that, when you have an average velocity, we have delta D over delta T. And well, since velocity is a vector quantity, well, so is acceleration, because acceleration is our change in velocity with respect to time. There's a delta T. Delta T and T are the same thing, by the way. Now, to find the change, this is a more familiar formula here that we're going to use right here. To find that change in velocity, well, you look at your final velocity and you subtract your initial velocity. So you have two different velocities, and when you subtract them, you find the difference or the change in them. All right, so again, this is the formula that we will most likely, well, we'll use the most this unit. All right, and so, well, here we go. And so we have, during a baseball game, it takes a baseball traveling at 24 meters per second north, in this case, 0.12 seconds to stop in a catcher's mitt. Determine the average acceleration of a baseball during the time that it is in the glove. All right, so we are looking for average acceleration, which I don't put A average, we just put an A. And again, it's a vector quantity, so it is going to have magnitude and direction. We don't know that. All right, now it takes, now I'm going to reread because we've got a word problem here. I'm going to reread the question and see what variables I have down. So again, during a baseball game, it takes a baseball traveling 24 meters per second north, that many seconds to stop. Ooh, to stop. All right. So here's what we have. This 24 meters per second north, that's what's called our initial velocity, VI. So I'm going to write that down, 24 meters per second. And again, because it's a velocity, it's north. All right. Now the final velocity, or our second velocity, it's same thing, is 0 because it's stopped. And again, when you have a 0 vector, that's the only time that you don't need a direction. And the other thing I have here is my delta T or T, again, same thing. So I'll write that down. We have my delta T, which is 0.12 seconds. All right. All right, so here's the formula I'm going to use, all right, where I have my VF minus my V1 or VI divided by delta T. Now, again, the key here is with directions when you're dealing with vectors. Again, I always put north as positive, the opposite being south being negative, all right? So when I substitute into my formula here, I have my acceleration is equal to, my VF is 0. Put a 0 in there. I subtract my VI, which is 24, and it's a positive 24, so I'll leave it as a 24 there, divided by my 0.12 seconds. All right, and let's see here. So on the top, well, that's just going to be a minus 24. 0 minus 24 is minus 24, divided by a 1.2. All right, and when I take those two numbers and I divide them, I'm getting a minus 200. My calculator here. Now, again, I want to write this vector down with magnitude and direction in units, all right, because I've done the math. It's piecing it all together now. Well, the magnitude is going to be 200. Now, your acceleration, the units here, we're dealing with meters and seconds. So your acceleration is meters per second squared. Those are the units for acceleration. Now, this acceleration also needs direction. And because our value is negative, again, I always have north mostly, I'll say 99% of the time. North is positive. Well, because south is negative, that means our acceleration is south. And so what's happening here is our velocity is moving one direction, but because it's slowing down, our acceleration is in the opposite direction. All right, now a common phrase in real life is it's decelerating. But in physics, you really look at it as you're accelerating, but in the opposite direction. So there's kind of words there, right? In real life, we would say the ball is being decelerated, slowed down. In this case, we are accelerating in the opposite direction. All right, let's try another one of those. Oh, big sports thing here going on here. All right, when a hockey player takes a shot with her stick, the velocity of the puck changes from 5 meters per second west to 13 meters per second east over a time interval of 0.04 seconds. What is the acceleration of the puck during the shot? All right, so once again, we're looking for acceleration here. All right, now the puck changes. So the puck is moving west, so that is going to be our initial velocity. So we'll put that in here. All right, so again, it's 5 meters per second west. Hands getting sore here. I'm not used to writing with the computer with the mouse. All right, so there's our initial velocity, but then the shot comes back. This is like a defense woman's shot here. The puck's coming back to the point. She then shoots it, and now our final velocity of the puck after the shot is now 13 meters per second, but it's going the opposite direction. 13 meters per second east. Okay. And the time interval, T. Our T value is, again, delta T, same thing, 0.04 seconds. All right, so again, I'm going to use my formula here. So I'm going to write it out where I have A is equal to my VF. VF, that's a terrible F. Sorry about that. Put a little tail on it. There we go. Minus VI. All right, all over delta T, or T. Let's just go with T. All right, so again, here's the key with today's lesson. Both of them is direction, right? Again, because of a compass rose, right? When I write it down here, never enter stinky washrooms. North is, or east is to the right, so I always say it's positive. West is negative. So my VF is going to be a 13. 13. That's a terrible 3, but apologize for that. There's a minus sign in the equation. But now my VI is 5. My initial velocity is 5 west. But again, I've said west is negative, so I'm going to put in brackets here a minus 5. All right, and again down here, my T is 0.04. All right. Now, when you have two negative signs come together, so grade 9 math, which I've taught a bunch, I'm going to have two negative signs come together, give me a plus sign. So I'm going to have 13 plus 5, which would be 18, divided by my 0.04. And I get a numerical value of, let me see here. Oh, it's not going to be a decimal. It's actually 450. But I'm not done here yet, right? So I got my numerical. What I have to do is make sense of that number. And so now I can write my acceleration down. I've got my magnitude is 450. It's positive. Meters per second squared. What do a lot of you guys do? This squared. I've seen people do that. All right. Now the direction, it is positive. I've said east is positive. So the accelerating is east. And there we go. There's our acceleration. So the puck was moving in one direction. This person took a shot, which made it go the opposite direction. So, of course, changing that direction so drastically, it had a very high acceleration and speeding up the puck to go in the opposite direction. But there's our acceleration. Let me see. I'm going to just check the chat for any questions. All right, looks good. All right, so now next up, here's a reason that I'm doing this lesson as a presentation is we got a graph. All right, so again, I'm going to find the acceleration of the skateboard for the first 10 seconds, the displacement. All right. So the slope of a velocity time graph is equal to the average acceleration of an object over a particular time interval. Now, here's the second thing we're going to use is that the area under a velocity time graph. And earlier today, by the way, the difference here is earlier today at 9 o'clock, we had a distance time graph. Here we got a velocity time graph. All right. Now, the area under a velocity time graph is equal to the displacement of the object over a particular time interval. All right. But we're going to use the slope here first to find our velocity, or sorry, our acceleration. All right. So again, using my graph here, well, 10 seconds, that's clearly going to be my time. All right, so there's 10 seconds. If I want to find my acceleration, I need a VI and I need a VF. It's one way to do it. That's how I did it this morning, probably the easiest way. And so in the first 10 seconds, which means, let's see here, there's my VI. And up here would be my VF. All right, so my VI, well, it's, and there's, this is velocity south, but it doesn't even matter with VI, my direction, because it's 0. And that's the only time, again, your vectors do not have direction. But my VI here, my VF here is 10 meters per second south. All right, so I can find that just using my graph, which essentially is I'm going to find the slope of my graph. So again, my acceleration, I'm going to use the formula I used before where I have VF minus VI over delta T, all right, which is 10. Whoops, I just put a T there. Ugh, arm's getting sore writing on this mouse. All right, so let's see here. Substitute in now again. Here's an example. The direction is south, right? And I've said that I always, 99.9% of the time, south is going to be negative for me. So VF is going to be a negative 10 minus VI, which is a 0. All right, divided by my delta T, which happens to be 10 seconds. All right, let's see. Up top, well, minus 10 minus 0, it's a minus 10. And down below, I have 10. All right, and let's see here. Oh, sorry, my VF, I wish somebody had said something up here. My VF, I go across here, it's actually 30. What the heck was I looking at? Feel free to correct me here, folks. So this, oh man, here, I'm going to just erase this. Let me see here. Let's go back. Oh boy, that's big. Boom. All right. So let's see here. So that's actually a minus 30 minus 0. Again, I don't have to change the bottom at all. You got to read your graph, even me here. Minus 30 on the top. All right, so that stays the same. Minus 30 minus 10 is a minus 3. But again, writing down my acceleration, I got to take into account the magnitude, the sign, piecing all the information together. Well, the magnitude of this is 3 meters per second squared. Whoops, shift squared. And again, this is a negative sign on my acceleration, which means the direction is south in this case, right? Because we're talking about north-south. All right, so there's my acceleration. All right, any questions? Let me look there. Nope. All right, so now we're on to the next part, the displacement. All right, now this is a little different, is that when we have a velocity time graph, which we do here, note number 2, the area under a velocity time graph is equal to the displacement of an object over a particular time interval. We're looking at 5 seconds here. All right, so that's our first 5. And so the area under the curve, under the graph, I should say, because it's not a curve, it's a nice straight line. Well, look what we have here, a triangle. And so the area, a little grade 9 math here for displacement is going to be base times height divided by 2 to find my displacement. All right, and so let me see here. The height is, let me see, I got my numbers right here. That has a height of 15. And let's see here, base of, well, 5. So height of 15, base of 5. So I'm going to go back. Base is 5. Again, I'm getting all this information in my graph. My height was 15 divided by 2. And let's see my numerical number here. 5 times 15 divided by 2. I get, oh man, I'm having trouble with my threes today. 37 point, let me see, 5. All right, so that's the number. Again, displacement, magnitude and direction going on here. So I have 37.5 meters. And let me see what the direction was here. I go up. We have to have direction here. This was all going south. There we go. All right, next up, same idea. What is the displacement of the skateboard after 10 seconds? All right, so again, I'm going to find the area under my curve. I'm going to clean this up a little bit. Let's get rid of all this. And so I'm looking for the area under the curve for 10 seconds. Here it is. So again, what do I got here? I got myself a triangle once again. All right, so I'm looking for base times height divided by 2. And so the base looks like here along is 10. All right, because we got the 10 seconds here. And the height, this time I'm not messing up, 30. All right, base times height divided by 2. So again, I'm going to go down to my displacement just like I did here before. Where I have my area. Again, my base was 10. My area, or my height, sorry, was 30. And divided by 2. And actually, I can do this in my head. 10 times 30 is 300. Cut that in half. I get 150. All right. And so again, that area is my displacement. So that gives me the numerical number of 150 meters. And again, the direction was south. There we go. So a little extra information that comes from a velocity time graph that we didn't have from a distance time graph. With a distance time graph, we could figure out the velocity, but with a velocity time graph, we can figure out not only the acceleration, but also the displacement of the object. There we go. All right, so let me see, stop presenting. Oops, stop everything here.